Hello everyone, good evening to all of you. It's currently 1:13 in the morning. I should be asleep by now, but I just wanted to get this quick thing on the notes of antibiotics in the sense of applied microbiology, the notes from the professor. I've been slacking on these, so I wanted to get one at least done before I go to sleep. Alright, enough of me yapping on. Let's go to the first slide that has the icon, the secondary metabolites. These are also seen as anti-tumor agents. Some of these secondary metabolites could intercalate between the double-stranded DNA bases. This will, of course, stop synthesis or transcription. Two examples of these anti-tumor secondary metabolites would be oh shoot, you know what? Let me change this for you. Sorry about that. Two examples would be our daunorubicin, and the other is dactinomycin. We also have bleomycin, and this actually destroys DNA by generating these oxygen-free radicals. These reactive oxygen species are actually caused by a ferrous ion in the bleomycin. Alright, let's talk about protease and peptidase inhibitors. So proteases are going to be essential in a lot of these normal physiological functions. One of the examples would be blood clotting. Elastase will be in the emphysema, and the processing of viral proteins will take place when you're talking about stress from disease. So we have elastase of emphysema and viral proteins. Protease inhibitors are produced by Streptomyces. And these are used for therapies. One example would be Bestatin. Bestatin will inhibit aminopeptidases, and so therefore it's going to be studied as a treatment for leukemia since it's able to inhibit aminopeptidases. Let's talk about the cholesterol synthesis inhibitors. Several products from our penicillin species will inhibit the synthesis of cholesterol. One of these would be compactin. Compactin, it's made again by penicillium. It lowers cholesterol by inhibiting the first step of the process. It was never marketed, however. We also have the aspergillus drug here called mevinolin, and this is marketed as lovastatin. That also stops cholesterol synthesis. All right, let's talk about the gram-negative cell wall. This is kind of a review here, but we have a very thin peptidoglycan layer, and then we have these lipoproteins. I'm going to write lip for lipoprotein. And then we have this big area here that has all these porin proteins called the outer membrane, also known as the lipopolysaccharide area. So these are just lipoproteins, these long integrals. So again, the gram-negative bacteria, they have this outer membrane. It adds this protection, kind of like a suit of armor. Small molecules less than 1,000 Daltons can pass through it. However, the water-soluble antimicrobials, which are greater than 1,000 Daltons, cannot pass. And then it just has low permeability to lipophilic molecules. Let's talk about some antimicrobial agents. This is going to be the beta-lactams. We actually looked at these last semester in the Gen Micro notes. So beta-lactams will inhibit peptidoglycan synthesis. And the peptidoglycan, its structure, remember we have these alternating chains of N-acetylglucamide and our N-acetylmuramic acid. These are the two alternating chains. We have the acetylglucosamine, and the N-acetylmuramic acid. They are going to be linked together by these peptide chains to provide strength and resiliency, basically. You combine with these penicillin binding proteins. They're called penicillin binding proteins because they just so happen to bind to penicillin. These are transpeptidases. From these links, they are going to actually form the peptide links in between the alternative chains in peptidoglycan. And since they just so happen to also bind penicillin, this is actually going to inhibit their actions. Again, it just so happens that they also bind to penicillin. So it's kind of like you're your own worst enemy type deal. Right, so this next slide has to deal with more beta-lactams. This is going to be the basic structure. This is going to be 6-aminopenicillinic acid, also known as 6-APA. This is going to have the condensed lactam ring, and then you're going to have this thiazolidine ring. So the thiazolidine ring kind of looks like a pentagon, kind of. It has this sulfur here, has a nitrogen in the corner, then it has some like groups off to the side like that. Beta-lactam ring, it's going to be like a square. And then you also have this acyl side chain here, the acyl side chain. It could be natural biosynthetic, which is the precursor was added to the fermentation broth. Or you could also have a semi-biosynthetic side chain, where it was removed chemically or enzymatically and then replaced with some other group. The penicillins are made by fungi, specifically Penicillium and Aspergillus species. Let's talk about the marcolides. So the marcolides come from Streptomyces. They consist of 12, 14, 16, or 17 member lactone rings with about 1 to 3 sugars glycosidically linked to these rings. There's going to be amino sugars and deoxyhexoses. So hexose is like a 6-carbon sugar. One example would be erythromycin. This is going to bind to the 50S ribosome. By binding to the 50S subunit, it blocks protein synthesis. All right, tetracyclines is the one that we're doing our presentation on later this week. Tetracyclines are made by Streptomyces. Specifically, a type would be streptomycin. You have 4 fused rings. Across all of the tetracyclines, they have this very interesting 4 fused ring system. You're just replacing the functional groups on them. They're going to be inhibiting the protein synthesis by binding to 30S ribosomal subunit instead of the 50S. Marcolides is 50S, tetracyclines are 30S. These are broad spectrum because they work against positive and gram-negative species. They're also hydrophilic, so they pass through the porin channels of the outer membrane in gram-negative bacteria. Next one is chloramphenicol. This is from Streptomyces venezuelae. This is easier to synthesize. It's very small. It's able to penetrate the porin channels due to its small size of less than 1,000 Daltons. And this one goes back to the 50S ribosome subunit, again inhibiting synthesis of proteins. We also have peptide antibiotics. This is from Bacillus. We're going to have these unusual D amino acids, and you have a very high toxicity, so therefore you can only use them topically. Usually used as food additives as well. They're too large, and they're also hydrophobic. They can't cross that outer membrane. Polymyxin, however, can cross. All right, let's talk about strain improvement. So the traditional approach would be random mutations achieved by spontaneous methods for S, X-ray for X, UV radiation for UV, and nitrogen mustard. This is like mustard gas. That's going to be NM. You then screen and assay. You screen by growing in medium, and then you assay for the antibiotic. So assay, antibiotic. So until recently, all of the improvements were accomplished by traditional approaches. Let's talk about the production now. This is going into the industrial side of things, the production of penicillin. Again, penicillium and aspergillus make it. It's going to be labile and acid. It's very sensitive to low pH. There's also a low toxicity to penicillin. Only 0.5 to 2% develop allergies. Fun fact, the professor in this microbio class, as well as one of my classmates, are allergic to penicillin, which is kind of interesting because it's a microbio class. Okay, so you combine them with those penicillin-binding proteins. Remember, those are just like transpeptidases that are there in the peptidoglycan. And when you bind to these the penicillin-binding proteins of the bacteria, this stops the transpeptidases involved in cross-linking. So you stop the cross-linking in peptidoglycan with the penicillin. Let's talk about the organism. This is Penicillium chrysogenum. It was improved by mutation, protoplast fusion, and recombinant DNA technology. Let's talk about biosynthesis. So this alpha amino adipate, this is a precursor of both the lysine and the beta-lactams. Excess lysine will shut down first enzyme of this pathway. However, so you need to make sure you note about that. Penicillin biosynthesis is also affected by the level of phosphate, glucose, and the ammonium ion. Lactose was originally used because there was glucose repression. So originally they would use lactose instead of glucose. Okay, let's talk about the feedstock. So the medium affected the type of penicillin produced. So if you're using something like corn steep liquor, this has a lot of phenylacetic acid, you're going to get penicillin G. Penicillin G has this benzyl side chain. It has like a benzyl ring as a side chain. Okay, and British fermentation, of course in the UK, they used a different medium and they got penicillin F. It doesn't have a benzyl side chain. Alright, more information. The nitrogen source, it could be corn steep liquor, soy meal or yeast extract, even whey. Carbon source would be lactose, glucose, or molasses. Lactose, again, was used because the glucose repression was happening. Phenylacetic acid, this is very important. This is for penicillin G. And then again, by playing around with nutrition, you could increase the level of biomass. That was like related to the research presentation that we did last Friday. Okay, just more information. The temperature is somewhere here. The temperature and the condition. So 200,000 liters. You have 0.5 to 1 aeration. Temperature 25 to 27 degrees Celsius. Duration is 120 to 180 hours. So the fermentation actually takes place in different phases. The growth phase, it's about 40 hours. This is where you're going to double every 6 hours, not 4 hours. Every 6th hour, you double. And oxygen supply is your strongest bet here. You need to make sure you work on that in the growth phase. All right, production phase. This is where you're going to reduce the growth. This is where the stationary secondary metabolites made. Feeding nutrients, you could extend this period. The production of a specific type of penicillin is controlled by adding the side chain precursor. So this is where you would also add the side chain precursor if you want to make a different penicillin. Okay, excretion of penicillin or the recovery of it. It's excreted by the cell, so less than 1% remains bound. You need to separate the mycelium, and then you're going to use the two-stage countercurrent extraction of the broth using amyl or butyl acetate as the reagent for that. The pH would be 2.5 to 3, very acidic. Temperature is 0 to 3 Celsius, and you get a 90% yield. Let's talk about semi-synthetic penicillins. Staphylococcus aureus has become penicillin resistant. This is also seen in hospital-acquired infections, and the Staph aureus was able to use this penicillinase from a plasmid. It was able to break up the penicillin, and therefore it lost its function. Initially, the 6-APA was produced in broths that lacked the precursors of the side chains. And again, the later penicillin acylase, this was used to cleave off the 6-acyl side chain. And then the 6-APA, the backbone of all these penicillins, could now be chemically altered. That's how they make new penicillins in this semi-synthetic method. All right, that's going to be it for tonight. Take care, everyone. Do something nice for someone, and good night to all of you. Take care.